All right, we're back. So let's take off from where we were. Any questions about NFAs and the power set construction?
So when you use an NFA, you say power set construction, you just say you should change that to NFA.
Yeah. So power set construction always means NFA. You make an equivalent DFA for it. Yeah. Any other questions? Sweet. So let's talk about something that you maybe have already heard of. They're called regular expressions. How many of you have used regular expressions before? Today. Yeah, they're widely used all over the place and widely misused. How are they misused? This term means so many different things in different contexts. So I had a student one time tell me that I have a regular expression that determines whether a number is prime or not, or like a binary number presented as input is a prime number or not. And something that we're going to prove soon is that the language of primes is not regular. Okay, so he sent me the link of where this came from, and I was looking through the documentation, and it said that when you have reached this particular point, reverse the input until you reach this point. So that's what's called a regular expression engine, and that uses something even more powerful than DFAs or NFAs, or what we're going to define as regular expressions. So something that you may intuitively have already learned about regular expressions is not going to necessarily be true here. We're going to have a formal definition of a regular expression here. And we're going to stick to that definition. All right. So what we're going to have is let sigma be an alphabet. And what we want to do is to try to describe the regular languages. And the way that we're going to define regular expressions is an inductive or recursive definition. So we're going to present some base cases and say these things are regular expressions. And then we're going to say if this regular expression is equal to two pieces where each piece is a regular expression and we combine them in some way, then that's also a regular expression. So just like question 3 on problem set 0, we're going to have a recursive definition. So then we say R for regular expression is a regular expression. If, then we're going to have 6 parts. Three of them are going to be the base cases, and 3 are going to be inductive. So if, no, I should say R equals A for some character A in this alphabet. So whatever alphabet you're working over, if it's just a single character from that alphabet, we call that a regular expression. Okay, super simple. Well, if I want the regular languages, what string do I always need to be able to recognize if I want the regular languages? Empty string. So if R equals the empty string. Again, very simple. What language do we always need if we want the regular languages? Along the same lines. Empty set. So if R equals empty set. So you may think this is super simple, and it is. So now we need to figure out, what other things would we need for the inductive part. Well, if you think back to the regular operations, so again, regular is used in a completely different way than regular expressions here. But what were the regular operations? Union, concatenation, and star. 3, 3. You think those 3 are going to go there? Probably. And that's what's going to happen. So if R equals R1 union R2, where R1 and R2 are regex, if R equals R1 concatenated with R2, or if R equals R1 star, where R1 is a regex. Okay, so we say that it's a regular expression if it is either one of the 3 base cases, or if it's one of the 3 inductive or recursive cases. So if it's the union of 2 regular expressions, we call it a regular expression. If it's concatenation of 2 regular expressions, it's also a regular expression. Or if it's the star of some, then it is a regular expression as well. Okay? Any questions about that?
And the star is the set of all.
Yeah, so it just means in this particular case, we'll define the language of a regular expression next. But the idea here is that you pick something out of the language of this regular expression as many times as you want, including 0 times. Star, in this case, just happens to be a character, but it represents 0 or more times out of the, yeah. Any other questions? All right, so then we define the language of a regex R. So if R equals A, if it's just a single character, then what should the language of that regular expression be? The set that only has A in it. Yeah. So then we're going to call L of R to be the set which only has the element A in it. If R is epsilon, then what do you think L of R is in this case? Set contains epsilon. L of R, epsilon. If R equals the empty set, what do you think? L of R would just be the empty set. So then L of R is empty set. So then we need to handle the base cases, the inductive cases. So if R is R1 union R2, then L of R. So what do you think the language of R would be in this case? The union of the languages of both of those regular expressions. So it's just inductively saying, if you know the language of these 2 guys, union them together, and then you get the thing that you want. If R is the concatenation of R1, R2, then what do you think L of R would be in this case? Exactly. R1, R2. And then finally, if R equals R1 star, then it's not too surprising to say that L of R is just L of R1 star. Okay. So it's just the intuitive idea of the definition of regular expression. So the language is just the set of strings that the regular expression describes, instead of where we had DFAs and NFAs, which is the set of strings that they either accept or there's some way to accept them. Whereas regexes, they describe a set of strings. So let's do an example. What I want is intuitively a regex for all strings in 0, 1 star that have, my handwriting's getting worse, that have the substring 101. Okay, so I want a regular expression that that describes all the strings that happen to have 101 as a substring. Okay, so this problem we came across in the problem-solving session we had on Monday. I recommend you go to those. But think about it. If a string happens to have 101 as a substring, what can appear before it? Anything? What about after? Anything. Huh. Well, how do we represent anything here as a regular expression? Well, first off, how do we represent 0, 1 star as a regular expression? I'll help you out. So it's 0 union 1 star. So pick 0, 1 as many times as you want, over and over. So that's just the set of all strings that happen to have, that's the set of all strings in 0, 1 star right now. But now I want the strings that happen to have 101 as a substring. So what should go next? 101. And what about after? 0 union 1 star. Okay, so this is just applying some of the definitions we had before. We wanted all the strings that before the 101 part, it could be anything. And we didn't want 101, then we wanted anything to appear after. All right. Any questions about that example or the definition? So what we did so far is we made DFAs, and then we showed with the power set construction that they're equivalent to DFAs. What do you think we're going to do here? Yeah, we're going to show that regular expressions are equivalent to the regular languages. So if I want to show that the languages of regexes are the same as the regular languages, if I want to show this, what do I better do? If I show that I can make a from a regex to a DFA, and what other way? Well, since DFAs and NFAs are equivalent, I only need one of them to help me here. But if I show regex to DFA and DFA to regex, are we done? Yeah. Yes. Will you let me use NFAs instead? Yeah, why? Because they're equivalent. I'm hearing more from here than over here. So participation is important. So if I show that the regular expressions are equivalent to NFAs in the sense that I can convert any regular expression into an NFA, and the other way around, then we're all good. Sweet. So let's do both of those directions. So let's convert a regex into an NFA. Well, let's see. Well, a regular expression, it must be one of these 6 forms, right? Can it be anything else? No, because it's the definition. So If I can make an NFA for each one of these 6 possibilities, am I done? Yeah, because if the regular expression is one of those things, then I just apply whatever procedure in order to make the NFA that we need to make. Okay? So let's do that. So let's handle the 6 cases. I'm going to need more space on 4, 5, and 6. Well, if R is just that single character A, can I make a regular expression? Sorry, can I make an NFA that only recognizes the character A and nothing else? Yeah, how do I do that? Well, if I tried that, if I did this, does that recognize the character A and nothing else? No. What does that recognize instead? A star in that case. Can I make an NFA that recognizes the single character A and nothing else? Make 2 states. So I'm going to make 2 states. And what's going to happen in between? Transition on A. Am I going to make any other transition? No. Does this NFA recognize only the character A and nothing else? Yeah. So that's pretty clear. So then we're going to make the NFA that thing. If R is the empty string, can I make an NFA that only recognizes the empty string? Yeah. So how can I do that? Well, I need to make 1 state at least. I should make it final. Should I have any transition? Do I need another state?
You could just do it yourself.
I mean, I could, but I don't want to make this any harder than I need to. Does this NFA work? Yeah, it recognizes the empty string. If I try to make any transition, I'm going to get stuck anyway. So this NFA recognizes only the empty string. That was easy. What if R is the empty set? Can I make an NFA for the empty set? Yeah, what do I need to do? Single state, just like before, but now it's not final. Like that. Pretty simple. So now we got to work on the 3 inductive cases. So the first case is if R equals R1 union R2. All right. So what am I assuming about R1 and R2 right here? Well, they're regular expressions, but what do I assume about that I have about them? I have an NFA for them, right? I'm assuming I do. So let's assume that I have an NFA for R1, and I have an NFA for R2. And let's say that the first guy happens to have a start state and 2 final states, and maybe this one has a start state and 1 final state. But it could be completely different in general. Could I make an NFA for the union? Yeah, it's something we covered last time. So how do I do it? New start state. And then what do I do with it? Epsilon transition to the original start states. Nice. That was easy. Let's do concatenation. So if R equals R1 concatenated with R2. Yeah. So again, I'm assuming I have NFAs for R1 and R2. Can I make an NFA for the concatenation of those 2 NFAs? Yeah, how do I do it? Make the final states non-final of R1. And then now what do I do? Epsilon transition where? Yeah, start state of the next guy. You see how this stuff kind of builds up over time? Cool. Did we do all cases? No, which one did I forget? Star. Cool. So if R equals R1 star, so now I'm only assuming that I have an NFA for R1. So let's say I have an NFA for R1. Oop, make those in black color. So how am I going to make an NFA for the star of this guy? Oh yeah, we needed to make a new start state because of our discussion last time. So I need to make a new start state, but should I make it final? Yeah, why? Empty string is always in the star of any language. So I'm going to make a new state that's final. And how am I going to connect it to the original machine again? Epsilon transition from where to where? Final states over here to the new start state. And then what else? To the original start state. And that's something we talked about also last time. So for all cases, did we just show how to build an NFA? Cool. So another thing that you should be noticing, I mentioned last time, but you should be noticing is that for the power set construction and this construction, did we need any intuition or some clairvoyance or whatever? Did we need some, trying to intelligently choose the right thing to do? These are completely algorithmic things a computer can do. Could you write a program to do this? Very much. Cool. So we were fortunate enough to actually do one direction. Do I need to do another direction? Yes, unfortunately. But before we get to that, let's do an example. So let's do the same NFA, the same regular expression, except I'm going to change it to be, it ends in a 1, 0, 1. Okay, that's fine. So if I ever ask you about how to convert a regular expression to an NFA, you must use the procedure that we have used here. You can't assume that, like, say 101 is a string, and then just say read 1, then 0, then 1. What you should notice here is that what are 1 and 0 in this regular expression? I think they're also regular expressions because of the very first definition. If it's a single character in the alphabet, it's a regular expression. So what you should be noticing here is that 1, 0 is not the string 1, 0. It's the regular expression 1 concatenated with the regular expression for 0. Okay? Sweet. So let's figure out how we're going to make an NFA for this. Well, what are the basic building blocks? Of the 3 base cases, which of the cases show up here? Well, union's not a base case. The single character 1 and the single character 0. Do epsilon or the empty set show up here? No. So the only one we need to worry about is building the basic block, just a single 1 and another one for the single 0. So let's build those right off the bat. not A, 0, 1. And then now, since we've exhausted all the possible base cases, we're going to be using these two NFAs over and over, and then just using the inductive cases over and over, using these two base cases. So what we're going to do first is we're going to build our regular expression from the ground up. So let's start with 0 union 1. How can I make one for 0 union 1? Exactly. So I'm going to have copy. And just like was mentioned, we're going to have a new start state that epsilon transitions our way over. So if I asked you instead that I want a regular expression for 0 union 1 and not say anything about using the method in class, you could, in theory, have two states, both of them, there's a transition from 1 to the other on 0 and another one on 1. So there are many ways you could make a regular expression, but the method specifies that there is exactly one way to do so. Okay? Well, we made one for 0 union 1. Let's beef it up a little bit. So I'm going to copy this down here, make it a little smaller. So now we're going to make one for 0 union 1 star. Okay, well, how am I going to make one for 0 union 1 star? Add a completely new start state. So yeah, new start state, make it final as like was mentioned. And what do I do? Yeah, epsilon my way in, and epsilon from the original final states of the NFA I was just given. So, of course, there are many ways you could have made a regular expression for 0 union 1 star, but using the inductive cases exactly, this is the one that you will actually make. All right? So let's do not the entire regular expression, let's do one more, or maybe two more. Well, the one we want to do next is, let's do 0 union 1 star with a 1 after it. So I'm going to cut and paste this again. And use another color. Maybe not that color, let's do green. All right, well, so think of this as the regular expression 0 union 1 star concatenated with the regular expression 1. So do I have a regular, an NFA for the regular expression 1? Yeah, so I need to put it in here. And then now I said, concatenate the one for 0 union 1 star with the one that we have for 1. How do I do that? Yep, make the former final states non-final, and we have 3 of them. And then what do I do? Yeah, epsilon transition from the original final states to the new start state of the second NFA. Oops, I don't want to keep erasing. So I'm going to have epsilon transition from here, and here, and here. Okay? Of course, as I've said before, you can make a smaller a smaller NFA for this regular expression. Why would I want to do this? Because I know for sure it's right. I'm not making any assumptions. I'm not trying to go on faith that this thing happens to be right. I'm not hoping it's right. I know it works because we have proven that the constructions for union, concatenation, and star definitely work. And so by applying this, it's not only that it's correct, and I know it's correct, it's completely algorithmic. So I can use my computer to make this NFA for me and not have to do it by hand. Okay? Any questions about that? Yeah.
If we were to add 0, 1 on the end, then we would just take the original construction, just tack them onto the end, right?
Almost. So let's try putting on, let's do purple. Let's put on 0 at the end. Well, so think of this as an NFA for the 0 union 1 star 1 concatenated with a regular expression for 0. Do I have a regular expression, an NFA for the regular expression 0? Yeah, so I'm gonna paste it in. And then now, since I'm doing concatenation again, what should I do? Yeah, make the final states of which NFA non-final? The first one, good. And then now what do I do? Epsilon transition from all old final states of the first NFA to the second. So something that a lot of students do, and it's wrong, is this. Right? That's not using the method of concatenating two NFAs. It's correct in the sense that the NFA that results has the same language, but it's not correct in the sense that it's not applying the method correctly. It's not applying the method of the definition of regular expressions. Okay? But if you have an epsilon transition in between, you are applying it correctly. Okay? Any questions about that? Sweet. So we proved one direction, which is nice, that we can turn any regular expression into an NFA. So therefore, the language of any regular expression must be regular. Why? Because an NFA, we can convert it into an NFA. But now, what do we have to do? Yeah, the other way. I got to show that every regular language has a regular expression for it. In other words, convert an NFA or DFA or whatever into a regular expression that has the same language. Well, that seems kind of hard because how do you extract out what the regular expression corresponding to an NFA is? Because it's just an arbitrary thing. Whereas for regular expressions, if we look back above, we had this clear and cut definition of what a regular expression is, and using the things that we've built up with, we can use the three constructions for union, concatenation, and star that we did for NFAs, and it just fell right into our lap. But this is a lot harder because NFAs, we don't know anything about their structure. We know nothing about it. We know that they have states and start states and transitions and whatever, but we don't know how the states are related to each other because they can be related in any way. So we'll need to think a little bit harder about this one. Well, let's see. What I'm going to say is not true, but let's suppose that it was. Suppose we had an NFA that looks like this. It's just a two-state NFA where R is a regular expression. Let's suppose that this is true. Why is this not possible currently? Can NFAs have a regular expression on their transition? No, they can only have a single character. So this is not possible yet. But let's suppose that it were possible. Well, what is the language of this NFA? Yeah, the language of R, right, because there's no transition coming out of the that only final state. There's no transition coming into the start state. So the only thing I could do in order to ever accept is just some string that R will describe. So the language of the NFA is L of R. So I'm assuming we could do this. And then we'll have a definition for generalizing NFAs in a second. But if we could have a generalized type NFA thing, where we have regular expressions on the transitions, and if I can whittle the states down all the way down to this two-state thing, then we're all set. Because I could just read off that transition and just say, yeah, that's the language of this NFA. And then we're all set. Okay? Any questions before we go into it? So I'm not going to make it through the whole construction, so we're going to do part of it today and then finish it on Friday. So in order to proceed, we need a generalized type of NFA. The name of it is a generalized NFA. So a generalized NFA. These things have other names, but the name we'll use is a generalized NFA. So GNFA for short. So we're going to be informal about this. So what did we want out of this? Do we want any transitions coming out of that single final state? No, because we want the language of the NFA to be whatever regular expressions on that transition. Do we want any transition coming into the start state? No, because if I had some way of getting back to the start state, then the language is not R anymore, right? So we need the following. Is an NFA, but has a single start state, which is no different, but it's worth repeating. Single start state, single final state. Other things as we're going to get to them. So single start state, single final state. Has no transition leaving the final state. Has no transition entering the start state. And the only thing that we needed otherwise was that there's a regular expression on all the transitions. And every transition is a regex. Oops. Okay. Single start state, single final state, no transition in leaving that final state, nothing coming into the start state, and every transition is a regular expression. Well, NFAs already have a single start state, so that's good. What about single final states? Do all NFAs have a single final state? No. So we need to work on that for a second. So, question. Can every NFA be converted into one with a single final state? Yeah, how? Yeah, something with epsilon. So let's say that we have this black box of an NFA. Let's say it has 3 final states. So what am I going to do to this NFA in order to make it have a single final state and nothing else? Epsilon, yeah, to a new final state out here. We better make sure that these guys are no longer final. And epsilon transition over. So it's kind of like concatenation, but not quite. Okay? So we can convert any NFA into an equivalent one with a single final state. And then you say, well, what if the original NFA had 0 final states? Could I just add a new final state not connected to anything? Yeah, would that change the language of that NFA? No, because it couldn't have accepted anything anyway. So the language is still the empty set in that case. So we can convert any NFA into one that has a single final state. Has no transition leaving the final state. Did we accomplish that? Yeah, we actually killed 2 birds with 1 stone in this construction because there's no transition coming out of that single final state. So that's already good. But I don't know if there's a transition coming into the start state yet. There might be one. So, yeah, make a new start state. Exactly. So we're going to do exactly that. So I think we accomplished that one. Is every transition a regex? Well, let's see. Is epsilon a regex? Yep. Well, what could have the characters been in the original NFA-M? It's either a character or epsilon. Are both of those possibilities regexes? Yep. So did I fulfill, or did we fulfill, every transition is a regex? Yeah.
I'm a little confused why you made the new start state and added an epsilon transition to the old start state.
Yeah. So
Doesn't that kind of count as having a transition?
No, there's no transition coming into the start state.
Oh.
Yeah. So the way that this is going to work eventually is that we're going to rip states out, and if we rip out a state that has a transition coming into the start state, then we need to handle that in some way. But if there's no transition coming in, we don't need to handle that. Yeah. So it's kind of like if you ever look at old cartoons and they have like this cloud, this dust cloud whenever they're fighting, it's like, I'm the start state, I'm getting away from all that stuff, and I'm waiting until the dust settles. So that it's the thing I always think of when I think of this. Don't question it. All right. But we can actually convert any NFA into an actual generalized NFA via this procedure, because we can just make a new final state, new start state, and a couple epsilon transitions. Any questions on the definition of GNFAs or how we can convert into one? Yeah.
Could you explain how you said every transition is a regex again? You said in the NFA.
Yeah. The NFA, remember, the only thing that could be on an NFA's transition is either a single character or epsilon. And those were the first 2 base cases of what a regular expression is. So they already are regular expressions. Any other questions, though? Okay, sweet. So let's work on an example and then see how we can get down to this 2-state thing where I only have a single regular expression coming from one state to another. So let's look at this one particular example and see how we could accomplish this. Okay, so this is an example NFA. Well, first off, we need to make sure that it actually needs to be a generalized NFA first. So the start state has things coming into it. So I need to make a new start state like before with an epsilon transition in. And you notice that, first off, there's only a single final state, so that's good. And there's nothing leaving the final state, which is also good. But I'm going to make a new final state anyway, because I want to be completely algorithmic about this. I don't want to have any intuition about this. So I'm going to make a new final state, just like we described earlier. Well, let's see. How many states do I want between that new start state and the new final state that I just made? I want 0, right? So I have 4 right now. Well, if I can remove 1 at a time and without changing the language any time, then if I can get rid of every single one of those, then we do have that 2-state thing that we described earlier, because there's no transition ever coming out of the final state and nothing ever coming into the new start state. So let's figure out, how could we get rid of that state in blue? Well, I want to not change the language anytime I delete a state. Should I ever delete the new start state or the final state I just made? No, because if I delete the start state, we're toast. And if we delete the final state, then we've destroyed any language we had. So I got to delete any one of the other states. So let's suppose I try to delete that one. Well, if I don't want to change the language anytime, what do I got to do? I got to figure out all the ways I could have gone into that state and make a transition to all the ways I could have gone out of that state. So for example, so I'll just copy this. So let's copy it right here. So let's suppose I actually deleted that state. And I'll leave the transitions in there for a second. Well, so what I'm going to do here, so if we observe these 2 transitions, this epsilon and this transition on A, I got to somehow keep that transition alive in the once I delete that state. Well, notice that it's coming from this state at the bottom and eventually ends at this state at the top, right? So since I deleted that state that I was originally referring to, well, it seems like we should have a transition from this state to that state on something. Well, we got to figure out what that something is. Well, how could I go from that state at the bottom to the one at the top using the state that was just deleted? How could I have used it? Well, how did I get into that state that I just deleted? Just a simple A. And I'll ignore a step that we should do in a second. Then how do I go from that state to the target state? Epsilon. Well, how do I put those 2 together? Concatenation. So what is A concatenated with the empty string? Just A. So I'm going to make a transition from the bottom state to the top state on A. And then now we have taken care of that transition. Was there another way that we could have entered the now deleted state and went out? Yeah, from the new start state, we could have epsiloned our way in and then epsiloned our way over to the target state. So what should be the final transition from the new start, from the new start state to this target state? Epsilon. Sweet. If there were 2 arrows coming out of the now deleted state, would we need to account for both of those possibilities? Yeah, so if there were 2 ways in and 2 ways out, how many transitions would I have at the end? 4, because there were 2 possible ways I could have chose to went in, and then 2 possibilities I could have chose to went out. I need to keep all existing transitions alive somehow. All right, so if we went on like this, let's try to delete that top state. So let's copy this again. So we won't be able to finish this, but let's say we tried to delete this state. And I need to keep that there. How many ways in to this state from somewhere else are there? 2, which is from the new start state and the one at the bottom. How many ways out to somewhere else are there? There are also 2. And you say, wait, what about that self loop thing? We're deleting that state. Is that self loop going to stay there? Like the actual loop, is that going to stay there? No. So, but we got to keep that loop in mind somehow. So I'll leave it at, actually we have 5 minutes, never mind. So let's suppose that since we deleted this state, I want to have a transition from the new start state over to here. Because that was a way in, and then a way out is to that target state. What should that transition be? Well, the way to get into the now deleted state was what? Epsilon. Now, what should I check? The self loop. How do I represent the self loop as a regular expression? A star. Or more generally, whatever the regex was, star, which happens to only be a single character here. So A star on the loop, then how do I get from the now deleted state to the target state? A. So the final regular expression is A star A. So we took care of that guy. So that was one way. Another way is from this new start state to the bottom state. Can anyone tell me what that regular expression will be? A star B. Because epsilon our way in, A star for the now deleted state, and then B to the target state. So A star B. So we've taken care of all the epsilon ones here. All right, so what are the only other possibilities? Is from the bottom state going to the now deleted state, and then 2 ways out of it. So let's do the one where it comes back to the now deleted state. What is it going to be on this bottom state? Self loop. It's going to be a self loop on something. What is it going to be? To get to the deleted state, we read A. Self loop on it is A star. Get back is B. So the final regular expression is A star, B. So we take care of that guy right there. Oh, I shouldn't delete that. It's the other one I should have deleted. Is there another way that I could have gone from that bottom state through the deleted state to somewhere else? Yeah, what is that way? It's going up, reading A, then A star, then A over to the state in the upper right. Oh, wait, that means I already have a transition from the bottom state to the target state. What should I do? Union them. So if I already have an existing transition there, and I want to have another way of doing the same thing, I'm going to have a union here. So it's going to be epsilon, union, what in this case? A star, A. And now we've handled all 4 possibilities. Let's actually go through the entire example. Oops. There are only 2 more states, which is nice. Could I have made any choice as to what state to delete? Yeah. So if there are n states that I am allowed to delete, there are, in fact, n factorial ways of making regular expressions. And as we have seen so far, there are many DFAs for the same language, and it turns out it's the same here. There are many regular expressions for the same language. So we just happened to pick one particular way to do it, but there are many ways to do it. So which state do you want to delete? The one with the self loop. All right, so let's try to delete that guy. So how many transitions am I going to add or try to put in? How many ways can I go in from somewhere else to that state? One. How many ways out? To somewhere else. It's always to somewhere else because I'm deleting the state anyway. So from what state to what state? From start state to the only black state left. We have A star A. Well, I already have a transition there. What should I do? Union them. All right, so I'm going to union it with something. So let's see. What is the way I could have gone from the start state to the now deleted state? A star B. So it's a good idea to put parentheses around things, but in this case, they happen to not be necessary. The self loop was A star B. How do I represent doing that self loop? The whole thing star. A star B star. Then how do I get from the now deleted state to the target state? Yeah, the epsilon thing. Epsilon union A star A. And it turns out that was the only way we could have went through, so now we can delete all our transitions. This is getting cumbersome, isn't it? Is there a way we could make this easier on us? How about let's call this a regular expression? So I'm going to call that monstrosity on that transition R1. So now we have this, so we only have one state to delete now. So let's try to delete it. And obviously we will only have one transition left. What is that transition going to be? Well, is it union? Is it union? Concatenation. So the transition actually is R1. Is this a regular expression? Be very careful. Is this a regular expression? No. You'd be very surprised how many students, when they're asked a question like this, and they'll circle that and they say, this is the regular expression. What's the regular expression I'm after? The thing on the transition. So the regex is R1. Okay. We actually carried through the entire thing, the whole construction. So next time we're going to formally define how to do this, and then we'll continue from there. So I'll see you on Friday. We'll take a 5-minute break. If you want to stay for an extra problem session, we'll start one in about 5 minutes.